Hello friends, today we will discuss a very interesting theorem on limit theory, and that is known as the squeeze theorem. Previously, whatever the limit theorem we have said, the techniques already we have developed or discussed thus far work very well for the algebraic functions. But we are still unable to evaluate limits of very basic trigonometric functions. And then the next theorem, that is called as the squeeze theorem, has been developed, and that proves very useful for the establishing very basic trigonometrical limits. The theorem allows us to calculate limits by squeezing a function with a limit at a point that is unknown between the two functions having a common known limit at a, that is a value. Now we can say the squeeze theorem as the comparative study of the limiting theorem also. So let's check what happens in the squeeze theorem. In the squeeze theorem, suppose fx, gx and hx be defined for all x those are not equal to the value a over an open interval containing the value a. If we have fx less than equal to gx and less than equal to hx, then for all x not equal to a in an open interval containing a and limit x approaching to a fx is equal to the limiting value L, and that is also equals the limit of x approaching to a for hx, then if we can say that the capital L, that is our limiting value, is a real number, then limiting value of gx when x approaching to a is also the limiting value capital L. Just like here, that hx is a function and fx is a function. Now at the value a, fx and hx both have the limiting value, that is capital L. Then we can say that gx has the same limiting value, that is L, at the x approaching to a. Let's check the squeeze theorem with an example. Apply the squeeze theorem to evaluate limit x approaching to 0 for x cos x. What is happening? Already we know that minus 1 is less than equal to cos x and less than equal to plus 1. So if we multiply the x with all these things, that means it is getting that minus x is less than equal to x of cos x and less than equal to x plus x. Okay, because minus 1 and plus 1 and in between the cos x remain, then for all x it is true. So we have minus x less than equal to x cos x less than equal to x for all x that is greater than equal to 0, and minus x greater than equal to x cos x greater than equal to plus x for all x less than equal to 0. Once again, if x is less than equal to 0, then x cos x belonging between plus x and minus x, and when x is greater than equal to 0, x cos x belonging from minus x to plus x. If x is negative, the direction of the inequalities changes when we multiply. Since now suppose we are thinking here that minus x less than equal to x cos x less than equal to plus x. So suppose that is our gx and that is our fx and that is our hx. So in that way we can say that when limit x approaching to 0 and for minus x, that we get the value as 0. Then for limit x approaching to 0 for plus x, we get the result 0. So that is our capital L. That means using the squeeze theorem, we can also say that the limit x tends to 0 for x cos x is also 0. So from the squeeze theorem we obtain limit x approaching to 0, x cos x is equal to 0. The graphs of fx is equal to minus x and gx is equal to x cos x and hx is equal to x are shown already in the figure. And according to the graph, already we can explain the squeeze theorem here. So once again, the squeeze theorem says that when fx less than equal to gx less than equal to hx for the open interval which is containing the value a, and we have limit x approaching to a fx is equal to L and limit x approaching to a hx is also the limiting value L, then we can say limit x approaching to a gx is also L, and that is our squeeze theorem.